Today we're going to be going over our next word prediction algorithm for our AAC board, and it used two main libraries, which is Word2Vector and GenSim, and here are some other dependencies that we have for this program. So the purpose of our program is pretty much to create an algorithm that can grab the next word in a sentence. So if I have a sentence, "Hi, my name is," well, the next word is going to be likely a name of a person. But I know this because I'm a human and I have 16 years of experience just living and being around other humans. How would a machine learning model know this? So that's where this model comes in. And in this, there's several different approaches. There's actually many different approaches to a next word prediction algorithm. A very simple choice is using something like an N-gram, which is what we have implemented here, to predict the next word based off of some training data that we've already provided. Meaning that if I have the word "my name is," then if I have like a data set that has many sentences from a conversation, then it's going to scan through every single occurrence of "my name is" in that data set, and it's going to look at all of the words that come right after it, and for the word that comes the most after it, that's going to be the best next choice. So over here we have a conversation data set from Kaggle that I will link below, and you can see if I do "my name is," I guess that's a bad example, but how are you, it's going to, how are, the most common word after that is going to be "you." And you can see over here that every single occurrence is followed by a "you." So in that case, the n-gram is going to pick up the probability of 1.0 of the word "you" following this, which means that "you" is the best option by far. Obviously, this data set is very small. It's only maybe 10 megabytes or something, so it's not the best representation. However, even with this data set, we found very nice results. So with that being said, we're going to be implementing something similar to that in this model using Python. So first, we're actually going to load the data set, and here's some basic pre-processing. First, the data set is formatted in a different way, an unconventional way. It's in a question answer format, and it's between two different people, so actually it is kind of convenient. I take back what I said before. So I can get the columns using pandas, so I can easily manage it using data frames. And the first thing I'm going to do is I'm going to remove every single contraction, and I'm going to replace it with the full form of the word. And the reason is because I'm producing this application so that we can have a grid of words for an individual to use to actually communicate easily with other people if they have motor and vocal capabilities. Now this entire communication is going to be facilitated through an EEG headset, and the application itself is going to be a 5x5 grid with many different words on it. So an example grid, that this is the initial grid that we're planning on having in the application. It's just this starter grid, and they can choose this word, and then the next words will be replacing it, and that will be the most common words, and so on and so forth. So that's kind of the premises of what we're going off of, and that's kind of why we want it to not have any contractions, because obviously that's going to be kind of making it much more specific than it has to be, and we want it to be simple words that a person could use so that they can still have a variety of words without having to struggle with getting the right word that they want. So with that being said, we're going to actually remove the contractions. Luckily, the Python contraction library does a very good job on this. There is another library that I forgot the name of, but it's a lot better because it uses NLP to actually deal with all this. However, that library has been implemented maybe 6 years ago, and it really was a hassle for me to get it downloaded and get it working, and in the end it did not end up working. So this one still does a really good job, and actually it does manage to ignore possessives. So my mom's dog, that's still going to be a possessive, that's not a contraction. It's not going to be "mom is," it's going to just be "moms" as in the English possessive form. So it does a good job for not doing anything with that, and you can see I guess you can't really see it here, but you can see that it just got rid of all contractions. There's no apostrophes unless there has to be. And then after this, we're going to use regex for some more pre-processing, and that gets rid of all the punctuations, everything. I just want only apostrophes so that it's only words left here. And you can see it did a really good job of doing that. After this, Word2Vector, which is the library we're using, it prefers lists of words. So I'm just going to do that as well. Now, finally, we're going to get to Word2Vector. So before I mentioned the N-gram approach, there's two approaches in this file specifically that we're using today. The N-gram approach, which is what I described before, is if I have the phrase "hi, how are," like "hi, how are," then it's going to look at all occurrences of that phrase. It's going to look at obviously all of them we saw before was you, so it's going to output you with a probability of 1, but in a more general example, it's not always going to be probability of 1, it's going to be other choices. And then if it can't find anything for that, it will move down to how are. And if it can't find anything for that, it'll move down to are. So the first was called a trigram, the second was a bigram, and the last one is a unigram. And that's kind of how it works. And here's a good visualization of what I'm kind of saying. So yeah, here you go. It's just like pairs of one word, and then pairs of 2 words, and then the pairs of 3 words. So yeah, that's pretty nice. Now, the second approach that we're using is Word2Vector. And this is a very powerful library. It's been developed for so many years. And what it does is it kind of maps each word to different like vectors. And computers understand vectors much better. Like, if I tell a computer thanks, it's going to look at me and be honestly confused. But if I say 0010, like any random numbers, it's going to understand that perfectly fine because it's programmed to do it like that. So what we're doing is we're assigning each different word in the vocabulary, which in this case is like 2,000 words, 1,000 words, 1,003 words, sorry. We're going to assign each different word a vector of length 300. And our goal is to have similar words to have similar vectors. I'll give you a basic example. If you can imagine a 2D grid, if you can imagine me saying the word US, like United States and Canada, they're going to be pretty similar to each other. But if I give United States and high school, or just United States and school, it's going to be pretty far apart. Now, obviously, this is only for one meaning, and words have many different meanings in many different contexts. So that's why we're giving it a vector of size 300, so that different words can form different relationships with different words given contexts. And that's kind of what Word2Vector does for us all completely. And you can see it's just only one line of code after all that pre-processing that does everything for us. And after this, we can use our model perfectly fine, which is fantastic. I'll also link a Medium article or just an article in general that taught me how to use Word2Vector. It's really phenomenal and very easy to follow. Finally, we're going to actually predict words using our two approaches. And here I've documented the different arguments and methods that we have in our word predictor class. We're first going to input all of our training sentences that we've pre-processed here in the list format that the Word2Vector likes. And then by default, we're going to choose the Word2Vector method. Otherwise, we can use N-gram. And here's another another value, an argument for our N-gram model to follow. Now, the Word2Vector, it works in a way where we just use a dictionary to have each word mapped so that whatever word is the best choice, it's going to have the highest probability attached to it. And in the same way, in that way we can either easily extrapolate what the best options are for our grid. And Word2Vector does everything, so it's a very simple implementation. After this, we're going to have N-grams, and this is going to be a bit trickier, but it's pretty much this one simple function that what it does is it looks for, given this context sentence, which is going to be, is it provided here? No, it's not provided here, but given the context sentence that's inputted, we can gather let's say the context sentence is 3 words long. It's going to find that entire context sentence in our data set, and it's going to create an N-gram for that, and it's going to look at all of the occurrences that come after that, and then after that, it's going to do the same for the last 2 words and then the last word. And the N-gram model, to make it faster, rather than searching up our entire data set over and over again every single time we have a context input, we just created every single possible N-gram from the get-go. So what this is doing is it's going to find N-grams of length, whatever the longest sentence is in the data set. Then it's going to go -1, -2, and then all the way until we have unigrams, which are just individual words. So that's what this code does. Finally, we're going to have the predict next word, and here is actually where the context is. That's my apologies for not realizing before. But the context, we can see that the Word2Vector handles it very nicely, and we can easily get similar words from that. And in our N-gram model, this is also daunting, but it's the exact same code from above, just copy-pasted. And what we do is, in our N-gram, we're going to find the largest n-gram that actually works for this context, and that's going to be our top choice. Because a longer n-gram with with a word following it is higher priority than a shorter n-gram. And in the worst case, like if we really can't find anything, we're just going to return the most common words. Right now we have it set as the most common words in the data set, but we can easily just revert back to our original conversation grid that we initialized before. So with that, we have our word predictor class set up, and now here's an example of us using this. So we have a very specific sentence, hi, how are you? And then after that, it's going to, like, the entire data set, half a probability of having doing following it, and half a probability of it, I suppose, moving on to the next sentence. So it's just going to be is, or, yeah, and yeah, that's it. And another example is he works, and we can see that it generates four different words that follow it. He works only in Canada. So yes, that's our entire implementation. I've tried to document it in comments, and it's going to be on GitHub. Thank you.